Welcome to the Bodhi Academy. My name is Amisha Plaso, and in today's video we'll continue with our class 11 chapter 6 equilibrium. So now in today's video we will talk about the ionization constants of weak acids and bases. Now we know weak acids are the ones we consider them to dissociate partially, or they have an incomplete dissociation that happens. They do not dissociate into their following ions completely. They dissociate partially. Now consider a weak acid, say HX, that is partially ionized in the aqueous solution. So the equilibrium can be represented by HX plus H2O giving us H3O plus and X minus. So what we are saying is that we have a weak acid, that is say HX. Now we are saying it is partially ionized in aqueous solution. So aqueous solution we have considered water, and then we are getting the hydronium ion and the X minus that is left over. Now if we consider their initial concentration in molar, we know the initial concentration is going to be 0 and 0 because before the reaction actually starts to occur. Then let alpha be the extent of ionization change again in molar concentration. So whatever change or whatever dissociation is happening, or how much ionization is happening, is denoted by alpha. Now if we can write it as minus C alpha negative Y, because this is somewhere getting reduced to form the products, correct? So this has a negative concentration into alpha plus C into alpha plus C into alpha. Now here if we have C as the initial concentration of the undissociated acid, HX at time t equals to 0. Okay, so initial concentration we are saying is C when it is undissociated acid, and HX at time t is 0 because initially there is no reaction that occurs. So alpha is the extent up to which HX is ionized into ion. So alpha is that extent to which HX is being ionized, as in how much it is getting dissociated into its respective ions. Now using this notations we can derive the equilibrium constant for the above discussed acid dissociation equilibrium. So now those were the notations that we are going to consider. C is the concentration, alpha is the extent of ionization, and Ca is the equilibrium concentration. So now using that we are going to define the equilibrium constant. So we can say that the equilibrium constant Ka equals to C square A square upon C 1 minus alpha. Now that if I further reduce, then I can get C A square 1 minus alpha. So we have Ca square, it is product, so we have this. Okay, so how do we write it? We write the concentration of product, so that is Ca into Ca upon the concentration of the reactants, that is given by C minus Ca. This if I have to write this C, if I take out common here, this I can write it as C 1 minus alpha. This is alpha. Okay, so that is how we are getting this C 1 minus alpha over here. Now if I further solve this, this will be C square alpha square upon this I can write as C 1 minus alpha. Okay, then if I want I can reduce this and this, so I'll get alpha C alpha square upon 1 minus alpha. So here Ka is the dissociation or ionization constant of acid HX. So this becomes the dissociation or ionization constant of the acid which is given HX. Now this can be represented alternatively in terms of molar concentration. So whatever concentrations we have taken, we can represent it in the same way, okay, with reference to the molar concentration. In that case we will get Ka equals to concentration of the H plus and Xi upon the concentration of HX formation. Now at a given temperature, say T, Ka is the measure of the strength of the acid HX. So now we are saying at say any given temperature which is there, T, we are considering Ka to be the measure of the strength of acid that is present. That is, larger the value of Ka, stronger is the acid. So now what we are saying, we are relating the strength of the acid to that of the equilibrium constant. So what we are saying is that if Ka, the value of Ka is larger, then we can say that the acid is stronger. If Ka is a dimensionless quantity with the understanding that the standard state concentration of all species is 1 molar. Ka, we are saying it can be a dimensionless quantity wherein it won't have a unit. In that case, we are saying why? Because if all the concentrations are at 1 molar concentrations. Now, the pH scale of the hydrogen ion concentration has been so useful that besides pKw, it has been extended to other species and quantities. Thus, we also have pKa to be the minus log of Ka. So, now initially when we were talking about the hydrogen ion concentration, that is when we discussed about pH equals to minus log of H plus concentration, correct? Now that theory was so useful that we extended it further for the other species as well. So here now we have taken Ka, that is the equilibrium constant for this dissociation or ionization constant it is called, that also can be related in the same manner. Now, knowing the ionization constant Ka of an acid and its initial concentration C, it is possible for us to calculate the equilibrium concentration of all species and also the degree of ionizations of acid and the pH of the solutions that is given. Now, let's look at what are the, in general, just let's go through the steps to evaluate the pH of the weak electrolytes that are present. So, first is to identify the species that is present before dissociation, that we identify it as the Bronsted-Lowry acid or base. So, first step is to identify which one is the Bronsted-Lowry acid or base. Second is the balanced equations for all possible reactions. So you have to balance down all the reactions, write them down, balance it completely. Then the next step is that the reaction with the higher Ka is identified as the primary reaction while the other is the subsidiary reaction. So we have to see which has the higher Ka value. Which has the higher Ka value, that becomes the primary reaction, that is the major reaction, and the other becomes the subsidiary, that is the secondary reaction. Now enlist in the tabular form the following values for each of the species in the primary reaction. So what we are going to do is we draw up a table, we note down all the concentrations. So first is the initial concentration, that is before the reaction occurred what was the concentration. Then we note down the change in concentrations on proceeding to equilibrium in terms of alpha, that is degree of ionization. Third is we find the equilibrium concentration. In step 5, now we substitute the equilibrium concentrations into the equilibrium constant equation for principal reaction and we solve it for alpha. Here we find the value of alpha. Now calculating the concentration of species in the principal reaction, last step we calculate the pH using minus log of H3O plus. Next, let's look at the ionization of weak bases. Now we spoke about weak acids, now we look into ionization of weak bases. The ionization of base MOH can be represented by the equation MOH breaking down into M plus and a OH minus, that is this one is giving away its electron to OH and therefore it has become OH minus and itself is becoming deficient of an electron. Now in a weak base there is a partial ionization of MOH into M plus and OH minus. Now the case is similar to that of acid dissociation equilibrium. So whatever we discussed about, there also we said that there was a partial ionization of the weak acid that was happening. Same case is happening here with reference to MOH. It is getting partially dissociated into M plus and OH minus. Now the equilibrium constant for base ionization is called as the base ionization constant. There it was called as the acid ionization constant and it is represented by K subscript B. Now it can be expressed in terms of concentration in molarity of various species in equilibrium by the following equation. So same way how we did for the above acid ones, we have to write the equation Kb equals to concentration of M plus into the concentration of OH minus upon the concentration of MOH. Alternatively, we say C is the initial concentration of the base, alpha is the degree of ionization of the bases, that is the extent to which the base ionized when equilibrium is reached. The equilibrium constant can be written as same basis, we have to write the equilibrium constant. So we are taking, it will be Kb equals to Ca into Ca, and then we will have in the base we have C minus A. From this, if we take out this C as to be common, we multiply C square alpha square, this is alpha. Okay, C square alpha square upon C, I am taking out common, what is left? 1 minus alpha. Here this C and this square C I can cancel, C alpha square upon 1 minus alpha is remaining. So that is what remains here, so as to be the base ionization constant. Now many organic compounds like amines or weak bases, amines are derivatives of ammonia in which one or more hydrogen atoms are replaced by another group. So now what are these amines? Amines are basically, they are derivative, they are part of ammonia itself. Here just the difference is that whatever the hydrogen strength is present in ammonia, okay, that is just replaced by one of the one other group. Okay, so say we have here pyridine. Okay, so here we have additional carbon over it. So these are such examples. Now ammonia produces OH minus in the aqueous solution. So now we have NH3 plus aqueous medium. So water, it is going to dissociate as NH4 plus and OH minus. The pH scale for the hydrogen ion concentration has been extended to get same way, pKb equals to minus log of Kb. Now let's look at what is exactly the relation between Ka and Kb, that is acid ionization constant and base ionization constant. Now in that, what did we see? That most of the things are very similar in both the cases. Even the formulas are at a point they are very much same, only it is the difference of H plus and OH minus that is happening. So as we have seen earlier in this chapter, Ka and Kb, they represent the strength of the acid or base that is present. Now in case of a conjugate acid base pair, they are related in a simpler manner, so that if one is known, the other can be reduced. So now when we are talking in terms of conjugate acid bases, we are saying that it is much simpler. So if you know the concentration, you know the value of one of them, then it is easier to reduce the other one. Let's consider a simple example of NH4 plus and NH3. Okay, so say we have NH4 plus you have water, it will dissociate to give us hydronium ion and NH3. Now over here Ka is going to be H3O plus upon NH3 upon the NH4 plus that is present. So here we are getting 5.6 into 10 raised to minus 10. Now let's look again at ammonia, NH3 plus H2O giving us NH4 plus and OH minus. Now what has happened? The reaction has basically proceeded so as to 10 raised to minus 5 we are getting. Okay, net, if I take out the net reaction of both of this, then I am supposed to get 1.0 into 10 raised to minus 14 molar, where Ka represents the strength of NH4 plus as an acid and Kb, it tells us the strength of NH3 as a base. Now, it can be seen from the net reaction that the equilibrium constant is equal to the product of equilibrium constants Ka and Kb for the reactions added. Thus, if we do Ka into Kb, then what will be there? It is actually basically just the product of these two. So here if I do this and this product, then I am getting 1.0 into 10 raised to minus 14. So the product of the acid ionization constant and base ionization constant matches the net reaction of the acid and base ionization constant. So we can extend and make a generalization here, saying that the equilibrium constant for a net reaction obtained after adding two or more reactions equals the products of the equilibrium constants for individual reactions. So what we are saying is that when you add two or more reactions, okay, that when you add the equilibrium constants of two or more reactions, the answer that you get, the value that you get is same as to when you multiply or you find the products of the equilibrium constant of the individual reactions. So K net is going to be K1 into K2, whatever how many equilibrium constants are being formed, if you find the product, that will always be equal to the K net. Similarly, in case of a conjugate acid base pair, say we have Ka into Kb equals to Kw. Now knowing one, the other can be obtained. It should be noted that a strong acid will always have a weak conjugate base and a strong base will have a weak conjugate acid. Now alternatively, the above expression, that is Kw equals to Ka into Kb, can also be obtained considering the base dissociation equilibrium. So we are here considering the base dissociation equilibrium. Say we have B plus H2O giving us BH plus OH minus. Same way, if we do, as the concentration of water remains constant, it has been omitted out. So water we are considering to be constant, so we don't really consider it. Then multiplying and dividing the above equation by H plus, we get Kw upon Ka, or it is, if you rearrange, you get K into Kb equals to Kw itself. It may be noted that if we take a negative logarithm of both sides of the equation, then the pKa values of the conjugate acid and bases, they relate to each other by this equation, that comes to be equal to the pKw equation. The pKw value is supposed to be 14, so when you do it, you anyway end up getting as 14 as the value. Now let's look at this di and polybasic acids and di and polyacidic bases. Now let's look what are these. So some of the acids like oxalic acid, sulfuric acid and phosphoric acids, they have more than one ionizable proton per molecule of the acid. So now if you have, let's look at sulfuric acid itself. Okay, so it is H2SO4. So it has 2 protons which can be ionized, correct? So in such cases where we have 2 or more protons which can be ionized per molecule, this is just one molecule of H2SO4. In this only I am having 2 protons which are ionizable. Now such acids, they are known as polybasic or polyprotic acids. The ionization reactions, for example, for a dibasic acid, say H2X, they are represented by equation H2X giving H plus HX minus. So here what is happening, only one of the proton is getting ionized, the other one still sticks to the initial one. Okay, then another step reaction, it becomes a 2-step reaction, then again the next proton is getting ionized, and finally we get the H2 minus. Now in the corresponding equilibrium constants are given as follows. So we will take this upon the product upon the reactants that are given, 2 we will have. Now here the Ka1 and Ka2 are called the first and second ionization constants. Why? Because here the reaction occurs in 2 steps. Why? Because we have 2 protons which are ionized, one in each step. So here we end up getting 2 ionization constants, first and second ionization constant respectively, of the acid H2 and X. Now similarly for a tribasic acid like H3PO4, we are going to have how many? 3 ionization acids, because here we have 3 ionizable protons, correct? So we are going to have 3 ionization constants. Now it can be seen that higher order ionization constants, say K2 and K3, are smaller than the lower order ionizations, that is Ka1 of the polyprotic acid. The reason for this is that it is more difficult to remove a positively charged proton from a negative ion due to electrostatic forces. Now what they are saying is that they are saying that higher order ionization constants are seen for Ka2 and Ka3, okay, and it is smaller as compared to Ka1. Now why is it? Because they are saying when you have only, now see, we had H2SO4 minus, okay, now if I remove from here one hydrogen, I'll have HSO4 minus and one H plus will go off. Now they are saying is that here there was a ratio of 2 plus and 1 minus was there, okay. So here the balance, the charge was more over here, charge was more, okay. Now but if you look now, here it is equally balanced. Now when you have equally balanced, what happens? The electrostatic forces which are there, they are working equally. Even if you try to pull it, this one will try to keep holding on, so it becomes difficult in that case. So that is why we see that this Ka2 and Ka3, they are smaller than the low order ionization constants of Ka1. This can be seen in the cases of removing a proton from an uncharged H2CO3 as compared from a negatively charged HCO3 minus. Here the charges are balanced. Here now what is happening? There is one positive and one negative charge. Similarly, it is more difficult to remove a proton from a doubly charged anion as compared to H2PO4 minus. So polyprotic acid solutions, they contain a mixture of acids like H2, H2A, HA minus and A2 minus in case of diprotic acid. H2A being a strong acid, the primary reaction involves the dissociation of H2A and H3O plus in the solution, which comes mainly from the first dissociation steps. Okay, so that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.